online assignments. Directions, you have signed, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things to be looking at. We had a curiosity happen last week. For some reason, items 5 and 6 did not appear on the Canvas page, but the links to item 5 and 6 were available to you from the sign-off list. So I'm going to quickly share this screen with you. So as you're looking at your week 5 online assignments directions and upload page, you will see that item 0 is your sign-off sheet. And there happens to be sine wave, video, horizontal portion of the sine wave, vertical portion of the sine wave, generating AC current, AC flow, AC conversions, function generator, the oscilloscope, how to do measurements with AC, how to do measurements with DC, and finally the most sophisticated part of oscilloscopes that we'll be covering this semester will be phase shift measurements with the oscilloscope. Now that won't happen for another 2 weeks, but being introduced to that now is really handy. So there's 12 items here. Could you verify that you can see all 12 on there, please? Thumbs up, good. All right, hey, it worked this time. Ha. Wonders. Okay, now separate of that, on this share screen, I want to open up the Excel that is associated. This is your Excel sign-off sheet, and the Excel sign-off sheet does in fact go to show 12 items. So they are the same, starting with sine wave, horizontal position, the sine wave, vertical position, the sine wave, and so on and so forth. So it all looks like that jives. All that is some of the first stuff that you want to be reviewing between now and Thursday. So we want to save Thursday for questions pertaining to your homework, questions pertaining to these concepts. Peek at these when you can make some time to look at it. All right, so that's enough of this particular part. Now let's go back to home and see on our PowerPoint. Let's see what else. Online, yeah, chapter, there's review questions, and then the challenges. Let me do the challenges with you first. Can you open up Lab 5 Basic and DC Challenges Upload? Can you open that up on Canvas, please? All right, so the gist of this is you're going to need to download the 2 zip files. So as you're looking at my screen, the very first one that we're going to do is going to be the Basic Circuits Challenge. You click on this guy, and what happens is you should see that the downloads go to the window bar, and it's in the zip file format. It downloads pretty quick. You double click this guy to open up the zip file. The zip file will then appear like so. And as it appears in this fashion, let me go ahead and close this other stuff, don't need it. So as it appears here in zip, you double click this guy. And what you're going to need to do is there is an exe file in here called electrical.exe. Right now, this is not usable yet. This has to be extracted, okay? If I go to double click this guy right now, yeah, see it says we're unable to do the executable. So what I need to do is the whole archive needs to be extracted. So no, I can't run this guy right now. So what I want to do is I want to click extract. Extract. And where do you want it to extract to? Make sure you find a convenient folder somewhere on your computer that you can easily locate. A lot of people like just putting it on the desktop. That way they can easily find it. So output downloads, it can go to downloads for now, and then we'll place it on the desktop. Now, I will go to download. So when all is good, what you end up with should be a folder that looks like this. Let me do view small icons. How about view large icons? Okay, you should see a folder that's marked Basic Circuits Challenge. That's in your download file. When you click this open, you'll see that the exe now has a symbol. When I go to click my exe, which is an executable file, what you will see, okay, can everybody see the Basic Circuits Challenge image on my screen? It shows that you have a total of 12 exercises to complete in the Basic Circuits Challenge. Each one of these, when you finish, results in a certificate of completion. You need to screen capture that certificate of completion. What does the certificate of completion look like? It looks like this. If I come back to here, let's go ahead and try one of these together. Let's go ahead and try Ohm's Law number 1. So if I double click on Ohm's Law number 1, it shows that there's a description that talks about Ohm's Law, reviews the formulas with you, and then you can begin. And so when you begin, you click the begin button, and in the begin, and this will vary from one student to another because it'll vary the numbers for one student. Can you see this now that I have 12 ohms and 1 amp?
Yeah, I see it.
Okay, cool. So Luis, I'm still waiting for a calculation. How many volts is this? 12 times 1, pal.
Oh, sorry, my mic was muted, but yes, 12 volts.
12 volts, okay. I'm going to put in here a different number. I'm going to intentionally type in 13 just because our button slipped on our finger slipped on the calculator. I'm going to hit grade, boom. And then it'll show you, does it show you the incorrect logo? Can you see the incorrect? Mm-hmm.
Yeah.
And then it tells you what the correct answer ought to be. So 12 times 1 is 12 volts and not the 13. Then you continue. And there's 20 exercises in each one of these pages, and there's 12 pages, so you have a few to do. So here's another easy one. You have 8 ohms and 5 amps. So Andrew, what's 8 times 5?
40 volts.
40, okay, I'm going to type in 40, and let's see if it gives us the right answer, and you are correct. And here's another one, 16, so we have 96 volts and 16 ohms. So could you give that to us, Jess? 96 volts divided by 16 ohms calculates to be how many amps?
1 second.
Sure, everybody need to have your calculators out and to have your cameras on. Carlos, I need to see your face. Everybody, I need to see your faces, so have your cameras on and have your calculators ready because you may be the next victim. I mean, volunteer.
6 amps.
So what do you have there, Jess?
6 amps.
6 amps. Cool. All right, let's go ahead and type in 6 and see what happens. And voila, it shows correct. Next one goes to show 36 volts at 6 ohms. I'm looking for current. So question goes to Ryan. 36 volts at 6 ohms. How much amps?
I got 6 amps.
6 amps. I'm going to type in 6 and see what happens. Oh, we're correct. Good job. And the next one is 12 ohms at 4 amps. I need a voltage. Shisamanga. I have 12 ohms at 4 amps. What is my voltage?
48.
I'm going to type in 50 just because. And it shows us, whoops, range. The first time I've ever seen it do that. Okay, next one goes to show 6 ohms at 6 amps. Harpreet, 6 ohms at 6 amps. How many volts?
36.
Okay, we're going to type in the correct number, 36, and it likes it. Let's continue. Next, we have 14 volts at 1 amp. I am looking for resistance. And the question goes to Erica. 14 volts, 1 amp. What's my resistance?
14 ohms.
14 ohms. I'm going to type in 14 and hit grade. Boom. Correct. We will continue. Next, we have 10 ohms at 3 amps. I'm looking for a voltage. So the question goes to Kirsten.
30 volts.
I'm going to type in 31 just to be different. Yeah, we know it should be 30. How can it do this? This is weird. There must be a margin of error. Okay. Next, 32 volts at 4 ohms. 32 volts at 4 ohms. Question goes to Javier. Javier, what is my amps? If I got 32 volts at 4 ohms.
8 amps.
Okay, I'm going to type in 15, some really wild number. Definitely incorrect, and it tells us we should have 8 amps. Okay, and the next one, we have 48 volts at 6 amps. I am looking for resistance. Question goes to Mr. Sepulveda. Frank, what do you got?
8 ohms.
Okay, we will type in 8, and it likes this. We're more than halfway through. Let's continue. 7 ohms at 8 amps. I am looking for a voltage. Question goes to Ephraim. 7 ohms, 8 amps. What's my voltage?
56.
56. Let's go ahead and type in 56. And great, it loves the 56. Cool. And the next one, we have 64 volts at 8 ohms. We are looking for current. Question goes to Toan. Toan, what amps do I have here?
It's 8 amp.
I'm going to type in 12 just because. And it says, yes, it's incorrect, and it should be 8 amps, which you are absolutely correct. And let's go ahead, and we have 8 amps, 5 ohms. Question goes to Abbas. Abbas, how much voltage do I have, Abbas?
You have 40.
I have 40. Type in 40, see what happens. Okay, we're happy campers so far. 6 more to go. We have 14 volts at 1 amp. I'll take this one. 14. Sure. Why the heck not? Next. Okay, 34 volts, 17 ohms. I need amps. Question goes to Kirsten. "34 volts at 17 ohms. Looking for amperage." Unmute your microphone.
Can you hear me?
I couldn't hear you.
Oh, 2.
2 amps. Cool. Type that in. It's happy. Cool. All right, just a few more to go. We have 28 volts at 4 ohms. Question goes to Greg. 28 volts at 4 ohms. What's my current? Unmute your microphone, Greg.
7 amps.
7 amps. Let's click that. It loves it. And we're almost home. 7 amps at 6 ohms. Question goes to Anna. I'm looking for voltage.
42 volts.
We'll type in 42 and it likes it. Okay, 2 more to go. We have 24 volts at 6 amps. Let's go ahead and type in the 4. And then the last one, we happen to have 18 volts, 3 ohms. I am looking for amps. Carlos Navarro, how many amps do I have? 18 volts at 3 ohms.
Okay, doing it now.
18 volts, 3 ohms. How many amps?
6 volts.
6 amps.
6
amps. Yeah, we're looking for amperage. Okay, so 6 amps. Yeah, we were given 18 volts at 3 ohms, so we're looking for 6 amps. Boom. Now, we've done all 20. Here's where you've got to pause for a moment because you need the certificate, okay? Everybody's still looking at my screen. I'm going to hit continue. It says exercise completed. Do not hit quit. Hit OK. And then enter your name. So I'm going to type in Ima Sample. Good old Ima. You don't have to enter an ID code. And what you want to do is you can click skip the disk storage. You don't have to store grade on a disk. So is everybody clear? You type in your name. You don't need an ID code. You don't have to store grade onto disk. You want to skip the grade disk storage, hit the red X, and error in name length. What do you mean error in name length? There's no error. But everybody see my certificate?
Yeah.
This, you can't see the certificate? Oh,
I know.
it's
I
paused. It's
can.
okay. It's okay. I'll come back to it. Hold on. Hold on. We'll come right back to it. It's right here. And boom. Now can you see the certificate? You need a screenshot of this because the screenshot of this shows your name, shows the name of the exercise that you just finished. So the name of the exercise was Ohm's Law 1. Name, I'm a sample. Doesn't matter the user ID. That's not you. The date was finished July 14th at 6:24, and the score was 85%. You need a minimum of 70% on each of these exercises, okay? So there's no Khan Academy this week, but there are these exercises this week. So what you do is you can hit print, and you can save it as a PDF, or you can also do this. You can do a snip. So I'm going to come up here, hit new, and I'm going to snip this guy. Boom. And open up a my Word document. Does that certificate have to occupy the whole page? No, that's a waste of paper. All I need to see is 6 certificates on the first page, 6 certificates on the second page, and that means you have completed all 12 of the basic DC challenge, the basic electronic circuits challenge, okay? If I come back to here, if I come back to this share, this one here, let's see if I hit print. Error printing, no. Yeah, it doesn't give you the choice of, on many instances when I hit print, I have an option to be able to create a PDF just so that I can archive the document. So in this case, it doesn't allow me to create a PDF. It immediately gives me an error issue. So my recommendation is do a snip and put it into a Word document or some other kind of document and call it a day. So we just finished Ohm's Law 1, and there happens to be how many in the Basic Circuits Challenge? There's a total of 12, okay? And so these are series and then parallel and then series, parallel, series sources. This is really, really good. You have to finish this, and you also have to finish the DC Circuits Challenge. And the DC Circuits Challenge will look like this. Let me get out of the share. Stop share. We've been rounding to the 100th. I think this one gives you a little more slack. If you round to the 10th, you should be okay with this application. Okay. And even if you encounter some kind of a hiccup like we've done, where we clearly put in a number that was, say, 1 volt off from the calculated value, it somehow accepted it. As long as your percentages are over 70%, we're fine. You don't have to keep, some people are very, very ego-driven, and they have to get that 100, and so they will pound on this 5-6 times in order to get it up to 100. You don't have to do that. Just get a passing score of 70%. We're happy, okay? Anyway, let's do this. Let me get to the other challenge. This is basic circuits, so I want to quit the basic circuits. I want to go to this other one. Close this guy, come here, and DC. All right, so now I would like for you to be able to see this guy. So can you see this new screen? This new screen shows DC Circuits Challenge. This is the other zip file. There's 2 zip files in Canvas that you have to open. And you get to practice more series circuits, parallel circuits, and series parallel. So there's a lot more that you get to practice. In this particular one, we will only assign up to series parallel 4. You won't have to do the last 2. You won't have to do series parallel 5, nor do you have to do basic networks, okay? So on the DC Circuits Challenge, you're only asked to do the first 10. Any questions about the DC Circuits Challenge exercises?
Is troubleshooting series circuits and troubleshooting parallel circuits?
No, none of those are assigned. Only the first 10 of the DC circuits and the first 12 of the basic circuits challenge.
Okay, thanks.
Yeah, none of the troubleshooting, nothing else is applicable. So we're looking for 12 plus 10, a total of 22 exercises that you're going to be doing. Okay?
Will this work on a Mac?
I don't know. I don't recall whether there was a challenge of this running on Mac, because this is executable on its own. So it's not like you download. So you can try it and see, but I don't recall whether it runs on Mac.
Because I had a quick, just experimenting with it, I wasn't able to open it on my Mac. So
On your Mac? Okay, then it's a similar challenge to those of you who were able to get around TI circuit building, okay? So for the exercise, you may need to borrow something that will allow you to run the program. Any other questions on this? Any questions about the certificates that you have to save? What happens if you zip along and you go so fast you forget to save a certificate? If you forget to save a certificate, then you have no proof that the task was completed, right? So do not lose your certificates. When you accumulate your certificates, keep your certificates in the order, same order that you solve your circuits challenge. So start from the top, work your way down, and then do the next column, start at the top, work your way down, so that your certificates will be in the correct order on your document. Okay. And so what you're looking at, let's go ahead here. So here's a Word document. Let's go ahead, quickly do zoom, scoosh us back over to here and share one more time so there's no misunderstanding. You're looking at my share screen, and this goes to show the Word document. And so you'll be able to fit like 6 per page. So first page is 6, second page is 6, third page is 6, and the fourth page is 4. So it's a total of 22. Okay. Okay. So let's go ahead and close this guy out and back home. Now let's take a look at our PowerPoint. Good stuff on the PowerPoint. It's a work in progress. I'm going to be adding to it in the next day, but the bulk of what I want to present to you is here. So let me go ahead and make this size. Okay. Can you all see my PowerPoint? Give me a thumbs up if you can. Cool. All right. Week 5. We are entering into AC. So before we can talk about AC, you have to talk a little bit more about DC and how DC is created, other than with a battery. With a battery, it's all chemical. But we also can create DC with a generator. So here's an example of a DC generator. And the DC generator, this guy is a video. So if I click on this guy and go to its link, let me catch its, edit the hyperlink. Select the hyperlink. Okay, starting at the beginning. Okay. So what we have going on here is south pole of a magnet, north pole of a magnet attached to pole pieces, which then there is a rotor. The rotor spins on a spindle, and the rotor has coils of wire around it. And as there is a magnetic field that happens between these pole pieces, between the red and the blue pole pieces, there are magnetic lines that cross from left to right between these pole pieces. Then as the wires are cutting through the magnetic lines, it generates an electrical current in the wire that is carried through to either bushings or something called a commutator, a ring, if you will, and carries wires over to these binding posts, which then attach to a light bulb. And it shows you the faster he spins it, the brighter the light bulb. The slower he spins it, the dimmer the light bulb. This is a very basic DC circuit generator. And all that we're doing with a DC generator is changing mechanical energy into electrical energy. So the mechanical energy of the big flywheel with the handle is attached via a belt to a spindle that has a rotor on it. And as these rotor with wires spin around in the magnetic field, electrical current is going to be generated in the wire that will be carried through to these binding posts. Now, the next, and we can go ahead and dispense with this guy for just a moment. And so it's not uncommon, and you may have seen this as an emergency generator for emergency purposes, and very often very popular in rural third world countries, is somebody gets on a bicycle on a bike stand and they pedal. And as they pedal, they are tied to a DC generator, which then charges a battery, which has a diode, which allows only current to come in one way. And then the charge from the battery goes into an inverter. And the job of the inverter over here is to change the DC into AC. And we're using AC to power whatever it is that you plug into an AC outlet. It could be a cell phone charger, it can be a lamp, it could be a refrigerator. Okay, so DC generator, we're taking mechanical energy into electrical energy. Here we have AC generators, and AC generators work on the same principle, except the windings and the way we extract the electricity off of those windings is a little different. We still have two magnets, a north and a south pole. And between the north and south pole, you can see the blue lines, which represent lines of magnetic flux, lines of magnetic energy between the north and the south. This rotor is a wire that is wound in a shape of a hoop. And as it's wound in the shape of a hoop, as it's rotating, these wires will cut across the lines, the magnetic field lines, in such a way that it will create a current that flows in the wire. That is known as the principle of induction. Induction, remember that word. Induction is the principle of being able to create an electrical current in the face of a face of a magnetic field. You will see the word induction and inductance a little later on in the PowerPoint. Next, in this slide here, it shows north and south pole, we have magnetic fields, and if we move a wire between the lines of flux, there will be a current that is generated in that wire depending upon the way that the wires move through the lines of flux. And as this is spinning between these two pole pieces, then the electricity is generated that comes out between two wires in the form of a sinusoidal waveform output. Now we'll talk about waveforms and wave shapes. Here are the wave shapes that you'll be interested in. We have what's known as a sine wave. There is a mathematical derivation as to how this can be calculated and plotted, but the shape is called the sine wave because it is based on the sine function. This is a triangular wave over here, looks like a triangle. This is a square wave. And this is something else they call a complex wave. So our discussions for AC will primarily be with the sine wave for the remainder of this semester. We have different kinds of circuits in class that generate the sine wave. We won't talk about how triangular waves or square waves or these other waves are generated, nor will we talk about where they're used. That's reserved for future electronics courses. Sine wave is enough for us to play with now. Next slide. Cool stuff. This ain't Tina. Tina can't do this. This is a different sim circuit, and this sim analysis is free to you. It is online, so it doesn't matter whether you have a Mac. It doesn't matter whether you have a PC. It can be used on a Mac. It can be used on a PC because the program is available to you online. We'll demonstrate this a little while later. But what you got going here is, instead of the DC voltage source that you're accustomed to looking at, we have a circle with a sine symbol inside. So this is an AC signal source. And it is marked with a polarity on top and a polarity on the bottom, only because it starts off, as you can see in the waveform, with a positive half cycle and then to the negative half cycle. So we'll be talking about this particular piece of software in a little bit, a whole lot of excitement around it. Now, on the oscilloscope, which is the instrument that we will be measuring waveforms, I have to talk about how to read the face of an oscilloscope. This is, on the right, the face of many, many oscilloscopes. The oscilloscopes are very often marked this way. And as you can see, on the right-hand side, the lettering at the top says horizontal axis measures something. What does the horizontal axis measure? Horizontal axis measures time in seconds, and it shows what we call 10 major divisions horizontally. So if you look at this large square here is called the division. So I have 1, 2, 3, 4, 5 to the center line, and another 1, 2, 3, 4, 5 to the right edge. So I have a total of 10 major divisions horizontally. And the horizontal axis measures what? It measures something called time. In what units? Seconds. The vertical axis measures something called amplitude, and in units of volts. And how many divisions is the vertical axis shown as? You have 1, 2, 3, 4 from the top to the middle, and another 1, 2, 3, 4 to the bottom. So it's a total of 8 vertical major divisions. Then if we magnify the oscilloscope and look a little deeper, you notice that the center vertical axis and the center horizontal line are graduated further with additional markings. And these markings are called minor divisions. And as you look at the minor divisions represented in these drawings, it shows that each one represents 2/10 of a division. So if this line here is a 0, then this is 0.2, this is 0.4, this is 0.6, this is 0.8, and this would be 1.0. Is everybody okay with counting the minor divisions? The minor divisions are 2/10 or 1/5 of a major division. Okay, this will factor to be very important for you to recognize when we actually read oscope displays. So let's go ahead and talk about some other definitions that you need to be aware of for the different parts of a waveform. Are there any questions so far? Okay. Next, parts of a sine wave. So the parts of a sine wave, there's two things. Now you will find in Unit 16 of your Del Mar textbook all this information. So your reading assignment is Unit 16, and then after you finish reading Unit 16 will be Unit 15, having to do with some additional math concepts. But Unit 16 talks about the electrical concepts, and it goes to show a sine wave in various degrees of its rotation. So when the sine wave is starts on the 0 line, horizontally, 0 line, and it is marked as 0 degrees rotation. When it rotates all the way up to the top, which is the positive peak, that is called a 90-degree rotation of the waveform. When the waveform continues rotating, it's like the top of the roller coaster, now coming down, it's coming down, and it hits the 0 line again, This middle horizontal line is called the 0 volts line. When the waveform hits the 0 line again, it has reached a rotation point of 180 degrees. When the waveform goes into the negative area, meaning below the 0 line, it's like way down here in the bottom of the roller coaster. When it hits the peak at the bottom, that is marked as 270 degrees rotation. And when it comes all the way back up, it is at 360 degrees. So one complete rotation of the waveform, what word did I use? One complete rotation of the waveform is marked as 360 degrees, okay? Next, other terminology pertaining to this, and you're going to need your calculators shortly, so have them handy. If you take a look at this, we have from the 0 line, here's our 0 line. From the 0 line, if this is at 0 degrees, and we go all the way up to the tippy top of the positive half cycle, that is known as your volts peak. So you have a positive volts peak up here. So this is your positive volts peak. And then you also have a negative volts peak. So there's a positive volts peak and there's a negative volts peak. And there's also something here marked as volts peak to peak, okay? From one peak all the way to the other peak. So if you know this half, if you know the positive half is 7 volts peak, and the negative half is symmetrically equal to that 7 volts peak, so the positive half would be a positive 7 volt peak, the negative half goes to negative 7 volt peak. What would my peak to peak be? What do you think? Andrew, you got a guess for me? Oh, Andrew had to get, Andrew just went off shift. Greg, do you have a number for me? If the positive volts peak is 7 volts peak and the negative goes to negative 7 volts peak, what is my peak to peak voltage?
I'm lost.
So Greg?
I'm lost.
Okay. Are you looking at my slide?
Yes.
And can you see this? Okay. So are you see where the mouse is hovering around? This is the positive half cycle. Okay? Everybody, this is the positive half cycle. And if I say that the positive half cycle reaches up to a 7 volt peak, that's as high as this is going to get from the 0 line up to the peak. And I also say that from the 0 line to the bottom of the negative half cycle is negative 7 volts peak. Then what is my difference between the very top of the positive peak to the very bottom of the negative peak? What is my volts peak to peak? Anybody?
14.
We would call that out as 14 volts peak to peak. It is simply a double of any one of these, okay? Because these will always be, for this semester, symmetrical. Whatever the positive side works out to be, the negative will be the same, except it goes in the negative direction, and the peak to peak is simply the double of one of these values, all right?
What would you read with the voltmeter?
Voltmeter is not used to read waveforms. A voltmeter will read something called RMS. So here's your RMS value. So the RMS value is along this dotted line here.
Like an average?
No, the average is a separate calculation. So we will talk about RMS as a separate discussion altogether. But your voltmeter is used to measure what's known as the RMS value, and your oscope is used to measure the waveform. You're going to need to understand how to convert the numbers from peak to RMS, and it's an easy calculation. Let me give you the short version now. RMS stands for root mean square, and I have that defined a little further down in here, interpreting waveforms. So RMS stands for root mean square, and root mean square, that part of the AC waveform is the amount of voltage to generate heat from a component that would be equivalent to the amount of voltage of DC. So a DC at 120 volts would generate the same amount of heat as 120 volts RMS. So your wall outlet is 120 volts RMS. Your wall outlet is this waveform. You can't read this waveform from your outlet because you don't have an oscope. You do have a multimeter, and your multimeter will measure the RMS version of this waveform. And I'll show you how to do those calculations. It's really, really easy. Okay. But the RMS is significant for us. It is not average. Average is a different value altogether. And RMS is, again, and I will add that to the slide between now and Thursday, give you a full definition of RMS and where it's significant and how it equates to the same amount of power dissipated by some kind of a load that would be equivalent to a DC voltage source. Now, let's talk about electrical terms and let's review these, because some of you, let's see, the very first four that we played with were these, yes? VIRP, voltage, current, resistance, and power. That's the first four. Then we introduced you to something called conductance, and conductance was measured in Siemens and Mohs, capital S or an upside down omega, and conductance was defined as the ease of flow of electricity and given to us by Ernst Werner von Siemens, a German engineer. Two other ones that we hadn't talked too much about, but they're part of your vocabulary, are these. Charge, which is symbol Q, measured in units of coulombs. Coulomb symbol is a C, and it gives you a very specific number of electrical charges. I won't get into either of the charge or work at this point in time, but these would be the initial electrical terms for the first half of our semester. For the second half of our semester, we have new electrical terms, and these new electrical terms are shown here. The very first one of which is a lowercase f. The lowercase f stands for frequency, measured in what units? Hertz. And what is the symbol for Hertz? Capital H, lowercase z. What is the definition of Hertz? Number of cycles per second, and given to us by Heinrich Hertz, a German physicist. We have lowercase t versus a capital T. The lowercase t represents time in the units of time in seconds, and it's a lowercase s. And how do you define time? I define it as the interval between events. I like that definition. I came up with that one. Yay. Next, capital T is the symbol for period, also measured in seconds. In the units symbol is the lowercase s for seconds, and it is called the time for one cycle, which begs for a definition. What is a cycle? Here's cycle. And the definition is given here. The part of a waveform from a start point through the rotation of that waveform to the point where the waveform begins to repeat itself. Very important, very simple definition, but very important definition. So a cycle is that part of the waveform where it begins and it rotates to where it starts to repeat. So if we go back to this image here, do I have a starting point? Do I have a rotation from 0 to 90 degrees, then to 180, then to 270, then to 360 degrees? Am I showing more than one cycle in this display window? The answer is yes. There's more than one cycle here. Okay, it looks like one and a quarter cycles is being shown here. On the right-hand side, how many cycles are being shown? One. And then if I were to show you this guy here, how many cycles are being shown? 3. I have a starting point. I have up to a positive peak, 90 degrees, down to 180, down to 270, down to 360. Once I hit 360, another cycle begins. So I have one cycle between here, and then a second cycle, and then a third cycle. So although this is one waveform, It is called a sine wave. It has 3 cycles in this particular illustration, okay? So that might give you a little better handle on the definition of the word cycle. The rest of these you don't have to worry about for a couple more weeks, but the very first 4 will be discussed this evening. So lowercase f for frequency in what units? Hertz. And what's the symbol for hertz? Capital H, lowercase z. Lowercase t is the symbol for time, measured in what units? Seconds. Symbol is lowercase s. Capital T is period, and that's measured in seconds, lowercase s. And what is period? Period is time for one cycle. And then I give you cycle. There's an interesting relationship that I have here as under also. That interesting relationship is here. Let me try to do it this way. I show you a formula that T, which is period, can be calculated if you know frequency. So if you reciprocate frequency, you can calculate T. Look at frequency. F up here, F is equal to the reciprocal of T. And we will practice those in a little bit, okay? Okay. Now, let's go ahead and try to play with a wave shape. So here is a wave shape. We're going to interpret the sine wave. All right, so we have reached the hour. I'm going to give you a quick 5-minute break. Get up, stretch. I'm going to put pause on our recording. Pause. I needed to record that. So let me reiterate these steps. In interpreting a sine wave, we follow these steps. We have to have a vertical scale. We have to have a horizontal scale, because these are your roadmaps that tells you how much each division is worth. So the vertical scale in this drawing is worth 30 millivolts for each division. The horizontal scale is worth 50 microseconds for each division. In step number 1, we count the number of major divisions vertically from the 0 line, the middle line is the 0 line, all the way up to the positive peak. We count 4 divisions in this particular case. In step number 2, you're going to multiply those 4 divisions times the vertical scale. 4 divisions times 30 millivolts for each division gives you a peak of 120 millivolts peak. So from the 0 line to the positive peak, we have 120 millivolt peak. The peak to peak is simply double that. So you take, step number 3, 2 times V peak will calculate to 240 millivolts. And you have to write the 2 little p's at the end of the volts peak to peak. Step number 4, we're calculating something called VRMS. RMS stands for root mean square. And that's calculated simply as V peak times the square root of 0.5. So you do 0.5 first. Then you multiply by V peak. And when you go to do so, you should be able to verify 84.85 millivolts, and you write down VRMS. This is the voltage that you will actually be able to show on your digital multimeter. The waveform is, we use an oscope to show the waveform, but the digital multimeter gives us the 84.85. Number 5 is your V average, and the V average is given as V peak times 2 divided by pi. And so it's 120 millivolt peak times 2 divided by pi gives you 76.39 milli V average. Step number 6 and step number 7, we're starting to count things horizontally. So step number 6, something called period. Period is given as the symbol T, defined as the time for one cycle. And we count the number of divisions horizontally for one cycle, which in this case is 8 divisions from left to right. Then we multiply 8 divisions times the horizontal scale value, which is 50 microseconds for each division. That will calculate the 400 microseconds. So that is the time. From the beginning of the waveform to the end of the waveform is 400 microseconds. Frequency is the reciprocal of period. So once we have the period of 400 microseconds, all we have to do is reciprocate that, and we will end up with frequency, and frequency is given here, calculated here as 2.5 kilohertz. Now, you get to practice with the next one. Here we go. The vertical scale is now given as 110 millivolts per division. Horizontal scale is 70 microseconds per division. I will get out a calculator and pen, and I will go ahead and do this with you. Let's start with volts peak. How do we verbalize, please, how we calculate volts peak, and walk us through the steps for number 1 and number 2. Could you do that for us, please, Harpreet?
So vertically is the scale is 110 millivolts. So we got 4 squares. So multiply by 110 comes out to be 440.
440 what?
Millivolts. MVP.
Yeah, millivolts peak is how we speak it. So far, so good. Your math is good. How many people agree we have 440 millivolts peak as our amplitude? So far, so good? Good. Okay, Anna, could you give us item number 3? How do we calculate number 3?
So I multiplied the 440 millivolt peak by 2 to get 880 millivolts peak. What does that stand for?
You want to speak it as volts peak to peak.
Peak to peak.
Good. That's how we speak it. All right. So in the sciences field, whenever we see this, we will speak it as volts peak to peak. We never run around and look at each other and smile and say VPP, VPP. No, there's no PP in tech. It's peak to peak. Okay. Okay. Anyway, enough of that. Good. So we agree that it's 880 millivolts peak to peak. Good. Could you walk us through number 4, please, Tony? Tony Ha, unmute your microphone and walk us through number 4.
Okay, so you use the VP times the square root of 0.05. So your answer is 77.78.
Not for this waveform.
Then I have 77.
It's okay.
I have 69.11.
Not for this waveform. Okay, let's put that on pause there, Tony. Tawan, can you explain to us how we should do number 4?
I got 311.13.
You're almost there, but can you explain to us how to do it?
That take 440 multiplied by square root.
No, you have to speak it correctly, Tawan. You take 440 millivolt
peak.
And then you do what with it?
Multiply by square root of 0.05 is about 311.13.
Good. 311.13 what? Apples?
I try to figure out.
No, the terminology is on there. The terminology is on the slide. All you have to do is
VRMS.
Correct. That's all you have to say. Perfect. Because we have to say the whole thing.
Sorry about that.
There you go, Tony. Okay, I'm glad you got it. You redeemed yourself, Tony. And thank you, Tuan. All right, is everybody in agreement? That's 311.13 milli-VRMS. You speak it completely and you write it completely. All right, so how about number 5? Jess, could you do number 5 for us, please?
So number 5 would be our volts peak, which is 440 millivolts times 2.
Yes. And then?
And you'll divide it by pi.
Yes.
Which So that's 280.11 millivolts average.
Excellent. Excellent. Well spoken. Everybody, you should be able to confirm 280.11 milli-V average. Okay, and you write down lowercase m, capital V for volts, and you write down lowercase avg for average. Any questions on the voltage calculations for 1 through 5 so far? Now we get to do 6 and 7. So step number 6, can you do this? Explain this to us, please, Luis.
Yeah, so first you have to figure out the cycle, and you look at the scale for that, and you see that a whole cycle has 8 divisions, major divisions.
8 divisions.
And then you multiply that times the scale, which was given as 70 microseconds per division.
Per division, correct.
And then so capital T equals 560 microseconds. That's what I
How
got.
many people concur that it should be 560 microseconds? Good job. Thumbs up. Okay, very good. 560 microseconds. Excellent. Thank you. Now, the next one, Erica, can you walk us through how we calculate number 7, please? How do we calculate frequency? Are you there, Erica? She might have stepped away. Dana, do you have an explanation for us on how to calculate frequency?
So I missed a little bit of the lecture, but I'll give it a guess. Calculating frequency. So you have the period, so you just divide 1 by the period, so inverse of the period.
Correct. And the period a moment earlier, your classmate calculated as 560 microseconds.
Oh, okay. So that would be 1.79 millihertz.
Look at your power of 10. Is it negative or positive?
Negative. Negative 3.
Did you key in your calculator 560 micro and reciprocate that?
Oh, no. Okay, so then that would be 1.79 kilohertz.
Precisely. Yeah, we have to key in the 560, and we have to remember micro as 10 negative 6. Once we key that in the calculator, then if you reciprocate that, then it comes out as 1.79 kilohertz. Okay? Is everybody all right with interpreting this particular waveform? Are we good with this guy? Okay, you get to practice another one. So have your calculators ready. I'm going to call a second set of volunteers for this one. So go ahead and work out. We have different scale now. Vertical scale is now 35 millivolts per division, and the horizontal scale is 90 microseconds. Different wave shape. Same wave shape, but different size and number of cycles. So let's go ahead and make our calculations.
Is that better?
Little, yeah.
Okay. What does volts peak to peak tell us?
Volts peak to peak just shows us whether or not we're going to exceed the scale of our display. And so by knowing volts peak to peak, there's certain settings on the oscope that we can magnify the waveform without changing its amplitude. So it simply is an indicator that lets us know what on the display we don't want to exceed. It's the most useful values to us are really going to be the volts peak and the VRMS and the period and frequency. Those are the 4 most important quantities. The rest is academic interest.
Oh, okay.
Okay, but the most practical application of values to us is your peak value, your RMS value, your period, and your frequency. Those we use almost all the time.
Okay.
Good question. Thank you. We have 4 times maybe. All right. Let's see how we did with these calculations. Erica, can you walk us through number 1 and 2 to give us the volts peak, please? How do we calculate volts peak, Erica? Are you back with us? Yes.
You count the number of notches up to the peak.
Okay. And how many do you count?
I counted 10.
Well, let's see. For step number 1, we're counting vertically. So how many do you count?
10.
We're looking at the major divisions, not the little ones.
Oh, so 2?
Yes, there's 2 major divisions that go from the 0 line up to the peak. So you don't count the little guys. The little guys are not part of our consideration in this particular drawing. So you count the major divisions. So 2 major divisions up to the peak. So what do you do with the 2 divisions?
You multiply it by the vertical scale.
Multiply by the vertical scale of 35 millivolts for each division. So how many volts peak do you calculate in this case?
70 millivolts.
You got to say peak at the end of that sentence.
Peak.
There you go. So how many of you agree we have 70 millivolts peak as our very first calculation? Thumbs up. Good job. Thank you, Erica. So the next question for item number 3, that would go to Ryan. How do I calculate number 3?
You would multiply 2 times 70 millivolts, and then you get 140 millivolts peak to peak.
Excellent. Well spoken. We will end up for item number 3, 140 millivolts peak to peak. Very good. Now for item number 4, Benjamin, can you walk us through how that calculation is made for number 4, please?
You take VP, which is 70 millivolts, and you multiply that by the square root of 0.5. So VRMS equals 49.50 millivolts VRMS.
Good job. Okay, so your volts RMS calculates to be 49.50 milli VRMS. How many people agree? Good job. All right, thank you very much. And then we want to calculate for item number 5. So item number 5, Mr. Sepulveda, can you get that for us, Frank?
I got 44.56 millivolt average.
Okay, well spoken too. That's 44.56 millivolts average. Okay, 44.56 millivolts average. Good job. Okay, for item number 6, period. Can you walk us through that, please, Carlos Navarro?
Oh, sorry, Professor, I'm not caught up. I'm sorry, I'm not set up.
Okay. Question goes to, let's say, Abbas. Number 6, how do I calculate period based on this slide? Look at the number 6 and read it out. And how do we do this?
So you do period is, so you count the number of since there are, and in the end I ended up getting 720, I think it's micro,
seconds.
Microseconds. Okay.
Yeah, time is measured in units of seconds. Okay, so read my directions for what it says for number 6. What does it say? Period is equal to a capital T. Are we good with that so far?
Yes.
Does it say it is the time for one cycle?
Yeah.
So you need to count the number of divisions horizontally for one cycle. How many divisions do you count?
8.
Wait. One cycle. How do I define
4.
one cycle?
One cycle. It's 1, 2.
Where the waveform begins. on the far left, up to 90 degrees, down to, look at my slide image. Right here is 0 degrees. It goes up to 90, comes down to 180, goes to a negative 270 degrees, negative peak, back up to 360. One cycle is a 360 degree rotation. I happen to have 2 cycles shown here. You don't count from here all the way to here because you're counting for 2 cycles. You only count for 1 cycle.
Oh, okay. So then it would be 4?
4 divisions. Are we clear on this, everybody? 1 cycle is 4 divisions. Now, based on this newfound knowledge, could you redo the math for us, Abbas? So talk to us. What do we do with the 4 divisions?
All right. So you take the 4 divisions, then you multiply it by the number given, which is 90.
90 what?
90 microseconds over divisions.
Correct.
4 times 90, 90. Then you get 360 microseconds.
Very good. How many people concur with 360 microseconds? Okay, that's what we should have, 360 microseconds. Thank you, Abbas. Well done. All right, so now, how do I convert that period into frequency? Question goes to Ephraim. How do I convert the 360 microseconds into frequency?
Hey, Professor, really quick, this is Carlos.
Yes.
Sorry, I think you might have said this already, but you keep saying micro, but that's not the right symbol. So that's what threw me off earlier. So I just kind of want to get back to that really quick. I know you probably explained this already.
What is not the right symbol, and where are you talking about? Because we have a number of steps that we talked about. Are we on number 6?
Let me collect and I'll get back to you then. There's like one of the symbols threw me off, but I'll talk to you on the side once I.
Well, no. Look at the horizontal scale. Let's take a moment. Look at the horizontal scale. In this slide, the horizontal scale is given as 90 with a lowercase u with a lowercase s. So that's microseconds. Okay, that's given. And
yeah,
our
thanks.
job,
I apologize. I just figured out my issue. I looked at the value on top of it, so we're good.
Okay.
Thank you so much.
Okay. Yeah, because don't get horizontal with vertical scales mixed up, because horizontal you go sideways and vertical you go up and down. All right, so let's go back to item number 7. So item number 7, could you, Greg, can you let us know how we determine number 7, please?
You take the value of number 6 and then you hit the reciprocal key.
Cool. And when you do that, what do you calculate?
2.78 millihertz.
Look at your calculator closely.
Well, I need to recalculate.
Well, okay. Yeah. That's our last calculation. And since that was our last calculation, there's no need to have cleared it to do anything else. Hopefully it would have been still on your calculator's display. But instead of a 10 negative 3, which you're calling out as milli, it's a 10 positive 3. Okay. So you have to be mindful. All of you have to be mindful of reading your calculators carefully when you key in these values and when you're reading the values. Any questions on this so far? Do you have confidence that you could do any and all of these that are coming your way? Guess what? You get to do another practice. You think you're so good. Here we go. Woo-hoo.
I have a question, Co.
Yes.
Would the major divisions be 2.5? Like for the vertical?
I don't think they're 2.5. You want to count that a little more.
3.5?
closely?
Sorry, yeah, 3.5.
Oh, there you go. Okay, you missed the whole square. Yeah, 3.5 would be a whole lot closer. If you put a straight edge, what you do is you get a piece of paper and you just put it as a straight edge. Does that straight edge line up with one of the hash marks, or does it kind of look like it goes in between? And it looks like the very tippy top of that red waveform goes in between 0.4 and 0.6. So if it goes between 0.4 and 0.6, yeah, I'd call that a half of a division. So yeah, 3.5 divisions is a good count.
And to make sure, would we count the horizontal divisions as 2.5?
Looks pretty good to me if you count it as that.
Okay, thanks.
Sure. These are all hand-drawn by me on a PowerPoint, so these are not actual waveforms off a scope. So I tried to make it as unintimidating as possible. Practice makes perfect on these waveforms. So we're just starting the calculations on this particular waveform. We have, looks like 3 cycles on this display. So how do we interpret these waveforms? You want to start with step number 1. So step number 1, could I please ask, Kirsten, could you do number 1 and number 2 for us, please?
Yeah. Can you hear me?
Yes, go ahead. We can hear you fine.
So, sorry. You take the number of vertical divisions, which was 3.5, and then you multiply it by the vertical scale, which is 15 millivolts, and you should get 52.5 millivolts, right?
Very good. Okay, that is entirely correct. We count the number of divisions from the middle line. The middle line is our 0 volts line. And from the middle, we count up. And the best that you can approximate, as I said, you want to take a piece of paper, you fold it in half, you create a nice straight edge, you lay it on your screen at the very, very top of the red waveform, the peaks, and it looks like we're counting from the 0 line to the peak, about 3.5 divisions. What do you do with the 3.5 divisions going up to the positive peak? You multiply that by the vertical scale of 15 millivolts for each division. When you go to do so, you should all verify that you should calculate 52.5 millivolts peak. Everybody concurs? 52.5 millivolts peak. Good job. Thank you. All right, question number 2. Question number 2 goes to Ryan. What do you have for number 2?
Number 2, I have.
Oh no, excuse me, number 3. Number
okay.
1 and number 2. Yeah. So what's number 3?
Number 3, I got 105 millivolts peak to peak.
Good. Everybody, we should be able to confirm 105 millivolts peak to peak. Everybody good with that? We just simply double the peak value and we get 105 millivolts peak to peak. Next, we want the VRMS value for number 4. Francisco Sepulveda, walk us through that, please? How would we do that?
So number 4?
Yes, sir.
You just want my answer, or?
Walk us through that.
Okay,
Explain it
so
to us.
I got my volts peak, which was 70 millivolts peak.
No, it wasn't.
Oh, wrong one. 52.5 millivolts peak.
Correct.
Then I multiplied that by the square root of 0.5. And I got 37.12 millivolts RMS.
0.052 times second square root 0.5. And you end up with what again?
37.12 millivolts RMS.
Okay, 37.12. Very good. All right. Times second square root 0.5. So 37.12 milli VRMS. Everybody? 37.12 milli VRMS. Thank you, Francisco. Well done. And
you're welcome.
The next one, how do I calculate number 5? And number 5 goes to Javier. Could you walk us through that, please?
You multiply VP, which is 52.5 times 2. Then you divide it by 3.14. Then you get a 33.43 V average.
33.43 milli V average. How many people concur with 33.43 milli V average?
I think I got 42, but maybe I round wrong.
Yeah, if you look at that more closely, it should be 33.42 milli V average. Okay, so watch that carefully. Your calculator does not lie. All right, just got to read it carefully. Thank you. Okay, so we have 33.42 milli V average. The next question for number 6, can you walk us through that, please, Anna?
So
Period.
cycle was around 2.5. So then I multiplied that by 125 microseconds per division, and I got 312.5 microseconds.
That looks pretty good. How many people concur with 312.5 microseconds? Okay, so we count horizontally. There's 3 cycles, but we only count for 1 cycle. And if you count for 1 cycle, it starts over here. Waveform comes up to a positive peak, back to 0, down to a negative peak, back to 0. This is the end of 1 cycle. So you count from here, 1 division, 2 divisions, looks like 2.5 divisions. So given that we have 2.5 divisions for 1 cycle, we take those 2.5 divisions and we multiply by the horizontal scale. Horizontally, it's 125 microseconds per division. So that will calculate to be 312.5 microseconds. Good job. Thank you, Anna. All right, so now we have one more step to do, and we get to play with frequency. And so for frequency, could you go ahead, walk us through that Toan? How do I do this, number 7, Toan?
I take 312.5 microsecond.
Good.
And hit the reciprocal. Then I have 3.2 kilohertz.
All right, the process is correct. We take the period of 312.5 microseconds, which we just calculated a moment ago, hit your reciprocal key, hit equals, and the display of your calculator should show you 3.2 kilohertz. Is everybody okay with 3.2 kilohertz? Thumbs up. Okay. Any questions on any of these 4 waveforms that we have just played with? The most interesting of which happens to be this one. Okay. Guess what you get to do next? You get to do an AC circuit analysis, and our friend, forever, our friend will be a VIR chart. The VIR chart stands as not necessarily the fastest way of doing things, but it is the most steady way of doing things because Ohm's law is what guides our VIR chart. So take a look at the schematic that we have. The schematic that we have is, okay, this would be a good time for our next 5-minute break. So I will go ahead and pause us here. I will put pause on the record. And could somebody please remind me in a moment when we come back from break to put the recording back on as soon as we begin. So let's go ahead and what happened to my share? Is my share still here? No, I don't want to share. And pause recording. That's what I want to hear. Okay, and now let's go to share. Go back to the screen of interest and share. Okay, everybody, you should be able to see very nice schematic. It's a series circuit, except it has an AC source. No big deal. It still is a series circuit. Everything you learned before about a series circuit is true for AC as it was for DC. What is the same in all parts of a series circuit?
Current?
Current is the same. So if you found one current, you have found them all. Okay? Series circuits divide something. What do series circuits divide?
Voltage.
Voltage. So that means this 10-volt source, and I made a notation here, this 10-volt source is a 10-volt peak source at 1 kilohertz. This 10-volt source will be divided across R1, across R2, and across R3. So part of the voltage will be on R1, part of the voltage will be on R2, part of the voltage will be on R3. So the principles that we learn from Ohm's law, Watt's law, voltage divider, current divider, all that holds true for AC circuits as well. The only difference is we happen to have a AC voltage source. So did everybody create a VIR chart? First thing you do is you create a VIR chart, and it should look like my insert here. Okay, you have a VIR chart. I just scribbled mine on a piece of paper. Yeah, that being done, what do you do with any VIR chart? Fill in your freebies. What are your freebies in here? Your R values and your 10-volt source. So R value, I have a 2 kilo ohm, I have a 3 kilo ohm, and I have a 5 kilo ohm. In series, I know that they should add. They add up to be 10 kilo ohms. I have a source, 10-volt peak, and you want to write that down as 10 V peak. Okay, 10 volts peak. And for now, we won't change to RMS. We won't convert to average or peak to peak. We'll just stay with peak just to keep things simple, okay? Okay. So from here, you want to finish filling out your VIR chart. You have your column of resistors, and you have a total voltage. What's the very first thing you're going to go for? The very first thing you're going to go for, question goes to Carlos Navarro. What's the very first calculation you want to go for?
Total resistors?
Okay, and what do you got for total resistors?
Sorry, 11. So yeah, 11 kilo ohms.
Well, if you got a 2, 3, and a 5, you got a 2, and a 3, and a 5. You're adding a 2, a 3, and a 5. Tony, what do you have?
10.
10
kilo
what?
ohm.
Oh, I'm glad you said it. 10 kilo ohms, okay? They're all in kilo ohms, so the answer's got to be in kilo ohms. So you just look at this, and let's use Mama's calculator, and it's 2 plus 3 plus 5 gives you 10. So it's 10 kilo ohms. So we have 10 kilo ohms for your total resistance. What would be the next step of what we would do to solve this? Andrew, what would be the next step? What do you, where would you tackle this now? He might not have settled in from commuting yet. Question, Harpreet, what would we do now?
Find a total amperage.
And how would you do that, sir?
Total voltage P divided by total resistance. That's a 10 kilo ohms. And comes out to be 1 milliamps.
1 milliamps. Very good. Okay, I don't know how this got on here. 1 milliamp. And how many people agree we have 1 milliamp? Good. All right. If you're happy with 1 milliamp, what would be the next step, Abbas?
The next step would be, I guess you could try finding R1's voltage or R2, any of them basically.
Well, we only filled in one cell, and that was current total. So
I guess would you, since isn't in a series circuit, I is the same, so would you put in like the 1 milliamps you got for total, you would put that in for R1, R2, and R3?
I was looking for that verbalization before you charged forth with anything else.
Oh, okay. Sorry.
Okay. All right. So yeah, you're used to working at warp 9, and I want to make sure I don't leave anybody behind. All right. So before you fill in the entire current column, because if you found one current, you have found them all. But what is the caution? I asked everybody that you should caution at this point. Before you go filling in that column, you want to make sure that calculation is correct. Maybe you should recalculate current to make sure your current is good. Okay, so 10 volts divided by 10 kilo ohms, you just do that again, and you confirm 1 milliamp. After you have the confidence that 1 milliamp is in fact a valid number, then fill in the entire current column of 1 milliamp, 1 milliamp, and now you have 1 milliamp filling in the entire current column. So that's what we want to do, is we always want to double check your RT, double check your IT before you fill in anything else. So now we have R column completely filled in, the I column completely filled in, and now we want to do the voltages. And very quickly, the calculated voltages question goes to Chisamaga. What are your calculated voltages for VR1, VR2, and VR3?
For R1, I got 2 volts.
2 volts.
For
Next.
R2, I got 3 volts.
3 volts.
And for R3, I got 5 volts.
5 volts, okay. That's pretty basic math, yes? And you just multiply current times ohms. There's a neat trick here. If some of you haven't seen this, when you multiply, if you look at your VIR charts, so your VIR charts should look something like this, yes? Something like this that I'm holding up to my screen. As you are looking at your VIR charts, and I'm looking at mine, the I times the R, don't you have 1 milliamp times 2 kilo? If you think about that, 1 milli is 10 negative 3. 2 kilo is 10 positive 3. The kilo and the milli cancel each other out. So all you have left is simply 1 times 2. And immediately there's your voltage. You don't even have to enter, when you're multiplying kilos and millis, kilo ohms and milliamps, you don't even have to key in the engineering. It's just a straight multiplication of 1 times 2, 1 times 3, 1 times 5. Okay. All right. So do we have this filled in? Do you have the confidence with the numbers? I don't have, I'm using a different computer, so I can't write on this screen like I can my Surface, but I wanted to try using a different computer this evening. And I don't think at any point in time in the 2 hours that we've been together has the microphone ever gone fuzzy, right? No fuzzy mics today. Yay. All right. That's a little victory. Now, I'm going to introduce you to something new and exciting. The slide that I showed you near the beginning of our time together, this one here is really, really nice. So as I said, I'm going to introduce you to a new piece of software that you use on the internet. It's not downloadable. You just use it right on the internet. So you can do this on a Mac, or you can do this on a PC. And this is a more robust program than Tina. It was good to learn Tina. It's good to have it. You can always rely on it for good basic circuit analysis. With this particular one, we can get into some AC and show you some waveforms, and we're about to do this. Let me show you how this is done. The site that we will go to is right here. It's called MultisimLIVE. So if you type in MultisimLIVE on a secondary screen in the address bar, you will be able to see this screen, MultisimLIVE, Discover Electronics, and it's got a yellow button for signing up, and it's got a green button for seeing how it works. So you can, if you want, hit the yellow button now. You can go ahead and sign up as we're doing this. It's very quick. So how many of you are on the MultisimLIVE screen? How many of you have it on some secondary screen? If you want to do it now, you don't have to do it now, but if you want to do it now, that's great. When you hit the yellow button to sign up for free, you will see this screen, which asks you to create an NI user account. Now, NI, I mentioned before, stands for National Instruments, And they make MultiSim, the full strength version. This one happens to be, some people call this MultiSim Lite. Yes, it's called MultisimLIVE. It's known as MultiSim Lite also. And so what you do is you create a user account. So you type in an alias, you type in your first name, you type in your last name, your status as student, your role as a student. The school is Chabot College. Address is not critical. Neither is city or postal code. But what is important, state, and then the graduation date, I put down December 22. Email address, I put down imasample9876@gmail.com. That is a valid email. It's one of my aliases. And you type in a password and you create an account. So it doesn't take very long to create an account. So how many of you who are creating an account are on your way to creating a user account? Okay. When you finish creating your account, the next screen that you will see is this. And we have features, circuits, resources. It shows who I am. I'm a sample. My identity is there. Role as a student. And there's a green button that next to it says, hello, I'm a sample. So they're saying hello to you. And you click create a circuit. So I'm going to create a circuit. So how many of you are actually doing this that would like for me to pause for a moment and give you a moment to catch up? Because you don't have to do it now unless you choose to do so. Okay, so we will click to create a circuit. When I go to create a circuit, the next thing that you will do is on an untitled circuit, you will see different parts of the screen, and it says you're going to click on sources, and then it opens up this dialog box of all different kinds of sources. We're going to click and drag the AC voltage source, click to select it, drag it out, click to place it, and then it'll go. Now I'm going to go to the site, actually go to the site, to new file. And let me maximize this screen. Okay, can everybody see my desktop for MultisimLIVE? Give me a thumbs up if you can see my screen. Okay, so here I have a number of different tools, very similar to Tina. These are main headers, and I look for the one that says sources. This one says sources. So when I click on this guy, it opens up a pull-out menu, and I look over here. I have a DC source, I have an AC source. I click on the AC source, I drag, and I want to place it, boom, right there. Once I have it there, I deselect it by clicking somewhere on the screen. Now it no longer has all the things around it. The things around it allow me to flip, allows me to make notations, allows me to rotate. I don't want to do any of those right now. I just want to place it. So now I have it placed. I'm going to hit magnify on this, make it a little bigger so you can see. Cool, nice. All right, everybody see a little better now? I'm going to come over here to passive devices, open up this window, and I've got resistor, I've got capacitor, I've got inductor. So guess what we're doing in the next 2 weeks? This is week 5. Week 6 and week 7 have to do with capacitors and inductors. Okay, so 1 week we're going to be playing with capacitors, another week we're going to be playing with inductors. So this software is perfectly set up to do the remaining labs for us. So I'm going to select resistor. I'm going to click and drag and place one here. I'm going to come over to resistor, click and drag another one and place it over here. Click and drag another resistor and place it over here. And nudge this guy up or move it up. Okay, deselect. And I'm going to come over here, schematic connectors, bring a ground, and I'm going to bring the ground over to here, let's say. So now do I have components placed on my board in a fashion that is similar to Tina? So far, it's very, very similar to Tina. Okay, just give these some spacing apart. Now, when I go to connect them together, it's a little tricky. Suppose I want to connect a wire from the top of the voltage source to the left side of R1. I come over here, and if I'm patient, give it a moment. In a moment, I will see what appears to be a pencil and a little rectangular block. The hand won't do me any good. I need that little pencil symbol. So double click. No, that won't work. Just have to be, there it is. Had it. Deselect a wire, come over to here, and now that's connected. And the next wire from here, got to deselect. Come on, be nice to me. Hover, there it is, and connect. Deselect, hover, there it is, connect, deselect, hover, there it is, come down here, and connect. Cool. And one more from here, hover, and come down and over and connect. Cool. Okay, so we have 3 resistors, we have a voltage source, and we have them in this sequence. We want to change our values, so I double click this guy, and way over on the right hand side, you see I've got 1 kilo. I'm going to select 1 kilo and change this to 2 and enter a K and hit enter. I now deselect. Now this is R1 is now a 2 kilo ohm resistor. R2, I'm going to double click this guy, come over here to the far right hand side, select the default value, type in 3K and deselect. Select the third one, select the default value, type 5 kilo and deselect. Confirm that I have 2 kilo, 5 kilo, 2 kilo, 3 kilo, and 5 kilo, as we did in the original schematic I presented to you. Double click the voltage source, and it starts off as peak voltage. I want to make this 10 volt peak, and it is now 10 volts. And how do I know it's 10 volt peak? Because here I have a choice. I can say peak or RMS. If I do this as RMS, type 10 and enter. Now the screen will actually show me 10V RMS. Now my voltages here can be measured with a digital multimeter. I don't want to do that. I want my voltages in this particular case not to be RMS. I want them to be peak. Still want it to be 10. Deselect. And so without any nomenclature after the 10, it's defaulted as a 10 volt peak. So right now this schematic is identical in value of voltages and resistors to the circuit I showed you earlier. I'm going to move this guy over here. I'm going to move this guy up here. And I'm going to hit grapher, waiting for data. Here's the schematic. I want to split. When I hit split, I can see an O-scope display, and I can see my schematic side by side. So that is accomplished by hitting this little split thing here. Over here, I've got a run simulation triangle, and I've got a stop simulation triangle. If I hit run simulation, and then over here, normally, let's see what we've got here. probe. Oh, silly me. I need a probe. I got ahead of myself. So I'm going to come over here, grab a probe, and I'm going to set a probe on this point. Oops, come here. Probe number 1 goes to this corner right there. I'm going to grab a probe number 2 and put this guy right here. And I'm going to grab a probe number 3 and put it right there. Okay. So now I've got 3 probes on my schematic, and look at where I've placed them. This one's a little bit high. I need to place it correctly. I want to place it on the wire. There we go. So I happen to have a green probe, number 1, placed at the corner between my voltage source and my first resistor. I've got a second probe in this lighter blue color placed between R1 and R2. I've got a third probe placed between R2 and R3. Now these are single point probes. Where's the black lead connected to, my friends? Ground. Okay, all I need to show is the red lead, the hot lead of my probe connected where I want. So what am I measuring here? Probe number 1 will measure the total voltage from here all the way to ground. Probe number 2 will measure the probe from the second and third resistor to ground. Probe number 3 will only measure the third resistor to ground. So let's see if these numbers will appear on our oscope display in a moment. I will come up and hit play. Nice waveform, whole lot of cycles, and too many cycles. So what I'm going to do is I'm going to come to my waveform display, and I'm going to change my time base. See my time per division controller? If I do this and do this, I've got too many cycles. So if I adjust my time per division button here, I can create an easier waveform for us to read. Yes? Nice. Very sweet. Okay, at this point, I'm going to stop the run because my waveform is nicely displayed. And let's go ahead and see if we can read how much voltage we expect at probe number 1. Probe number 1 measures the total voltage across all 3 resistors to ground on this side. Probe number 1 also measures the voltage source from this point to ground on the left side. What is my voltage source? Is my voltage source 10 volt peak? Is the probe green colored? Can you see the green waveform on my display? Can you see what the peak value is if I hover my mouse over this? And notice I can't get my mouse right to the tippy peak, but if I put my mouse right here, can you see 9.9849 volts? Is that pretty close to 10 volt peak? I'll show you something even more interesting. Suppose I now go to the last one, probe number 3. Probe number 3 measures the voltage across the third resistor to ground. What was your calculated voltage for VR3 to ground? Wasn't that 5 volts? Did we calculate 5 volts peak on your VIR chart? And if I hover right here, is my hovering on the screen pretty close to 4.95, 4.99, pretty close to 5 volt peak, yes? Okay. What do you think will be the voltage from probe number 2 to ground? On this side, I've got the sum total of V voltage across R2 and the voltage across R3. What did we calculate the voltage across R2 to be? Wasn't that 3 volts? And wasn't this 5 volts? So from the light blue probe, probe number 2, going to ground in this direction, should we expect 8 volts? And that's the light blue probe at probe number 2. And if I hover here, am I pretty close to 8 volts? It shows me 7.9879. That's pretty close to 8 volts. Isn't that amazing? Now, I'll show you something else even more amazing. On the left side of my screen, there's an area called cursors. Right now there's none. If I go ahead and pull this guy down and I select cursors on the y-axis, it automatically gives me 2 cursors. If I move cursor number 1, grab cursor number 1 and pull it all the way up to the top of this, is there a voltage reading for cursor number 1 down here in the lower left-hand corner of my O-scope screen? Is cursor number 1 shown as a bright green? And is cursor number 1 shown as 10 volts? Because I've laid this cursor line right at the tippy top of my green waveform. We start off with a 10 volt source, 10 volt peak source, and we confirm 10. I'm going to place cursor number 2. I'm going to grab cursor number 2, and cursor number 2 I'm going to place over here at the top of the light blue. And while it sits here at the top of the light blue, which is at this probe, does cursor number 2 show me 8 volts down here? Does the O-scope confirm our calculations with Ohm's law? It's pretty amazing. So we use the O-scope to confirm the peak values of the waveforms, and we use a digital multimeter to confirm the RMS values. Okay. So any questions about how to, let's go ahead and confirm this last one. I'll move the cursor number 2 to the tippy top of the blue waveform. And what's cursor number 2? 5.0435. Pretty close to 5. We're happy with that. And even without the cursors, my friends, I'm going to move the cursors completely off the screen. Do we have markers on the vertical axis? Does it say voltage? Does it say 2.5 volts here, 5 volts here, 7 volts here, 10 volts here? Does the axis marking confirm that green waveform is hovering right at the 10 volt line? Okay. Does it confirm that the dark blue curve is hovering peaking right at the 5 volt line? So without the cursors, we can still use the division markers to be able to tell us how much voltage these waveforms are displaying. But when you have something like that light blue waveform that's in between 7.5 and 10, it's kind of hard to approximate. We can use a cursor, grab either 1 or 2, doesn't matter. I'm going to grab this one, lay it right down on the tippy top of the light blue waveform, and hover right about there. And we expected 8 volts, and guess what? We measure 8 volts. Pretty cool. Now, how about period? How do you count period? Well, you count it this way. You count it as the amount of time between the beginning of the waveform to the end of the waveform. And do we have a time mark? Do we have, let's see if I come this way. Oh, we came quite a ways. It doesn't matter. Okay. Okay, now it's in the middle of the display. That's fine. Do we have a starting point right here for all the waveforms? They're all in phase with each other. They're just showing the values at measuring at different points of the circuit. Do we have a time mark here? What is the time mark here? 27.457. Where is it on here? Aha, here we go. It shows us the number of microseconds per division right here, yes? On the bottom of the screen, it shows us 200 microseconds per division. And it shows us this while we are in the run mode. If I go to pause this, this will show where the waveform stopped over a period of time. I need to have this in the run mode, so I hit my little run triangle, and do we see 200 microseconds for each division? Now, could you count with me the number of divisions from the beginning all the way to the end of one cycle. So how many divisions do you count here? Andrew, how many divisions do you count? How many large squares do you see between the 0 over here to where the one cycle ends?
Ask me that one more time.
Okay, the number of horizontal squares between where the waveform begins on this side, following this line, to where the waveform, the cycle ends on this side.
I count
How many-
5.
I count 5 squares. Does everybody agree we have 5 divisions? And what do you do with those 5 divisions right now on your calculator? Multiply by 200 microseconds for each division. So do that now. Take your calculators, turn them on, clear, 5 times 200 micro, and hit equals. And what does your calculator display in terms of time for one cycle? The time for one cycle calculates to be what value? Question goes to Tony. Mr. Ha, what do you calculate? Tony Ha.
Yeah, I'm here.
Yeah,
One
so
milli. Let me see. Time is 1 millisecond.
1 millisecond. How many people agree with 1 millisecond gives us a thumbs up? While that number is on your calculator, that is the time for one cycle. There's a quick 2-button push to convert time into frequency. What do? You hit your reciprocal key,
1
and then you
kilohertz.
hit equals. And what is the frequency that you calculate, Gregory?
1 kilohertz.
1 kilohertz. And does that confirm our source frequency at the very beginning? We said this would be 1 kilohertz, and we got 1 kilohertz by measuring right off the display screen. Yes? This is a really, really powerful piece of software. This will be one of the assignments that you'll be doing, and other lab assignments similar to this using this piece of software. And as I've said, this piece of software is an online software, so it doesn't matter whether you're using a Mac or whether you're using a PC. Everybody will be able to use this software to be able to generate these wonderful waveforms and confirm these values. So we went through this exercise together. We went through the exercise of this circuit. We did a VIR analysis of this circuit. We filled in the VIR table for this particular circuit. We had predictions for voltages across each of these. We put in test points, and from each of these test points, we have an expectation how much voltage to ground, and we were able to display a waveform that confirms those voltages to ground. Is everybody okay with this demonstration? Would you like to see one more?
How do you get those cursors? I made that whole schematic for the circuit.
Mm-hmm.
My cursors are gone.
Your cursors are gone. Well, first of all,
after I split.
Okay, so while this is running, you have a cursor control on the right-hand side, which you can flip. So the arrow points, you want it to point down to open up the cursors, and then you pull down here. What type of cursor do you want? You want the x-axis cursor? X-axis cursors go this way. If you want the y-axis cursors, which is what we were using, they go this way. If you have a track, we're using, this allows us to track points. We're not using that particular one just yet, but let's stay with the y-axis. So you have to open up the cursor control panel, select y-axis, and then you have your cursor 1 and you have your cursor 2. So cursor 1 and cursor 2. And so we can, once the cursors appear, then you grab them and you can place them anywhere you want. So if I place this guy here, cursor number 2, at the tippy bottom of the light blue waveform, we expect negative voltage. Does it show me in this window underneath cursor 2, I have a negative 8.0012 volts? Yeah, I expect the negative voltage, and it reads out as a negative voltage. Okay. Are we good with this particular guy? So once you do this, hold on, don't get excited. We did a lot of work. What you ought to do is in the file navigation menu, which is this crisscross up here, select this. Oh, you got to stop the circuit from running. Okay, once the circuit is stopped, then you select this guy and you do a save as. So please do a save as. And when you do this as a save as, this, and you put in the title of the circuit, this will be capital AC, 3 capital R, because there's 3 resistors, and your name or initials. I'm a sample. Okay. So AC 3 resistors, I'm a sample. And then you click OK. And now it will become part of your library. So if you go up here and we want to see other things, we can see other, you will be able to see other things that you've built. I'm going to do one more new one. Actually,
Professor, I have a question.
Yes.
Does this do a triangle and square functions?
I haven't seen it do this yet. I haven't played with it enough to see whether it does. Again, this is a watered down version of MultiSim, which is what we use in the classroom. And MultiSim in the classroom does just about everything. But I'm so excited that this is able to do sine waves and gives us waveforms and gives us the ability to be able to read the waveforms and verify the predictions that we make on paper. So
this is amazing. Thank you. Yeah.
Yeah. So, and it's free, and it's not platform specific. You can use this on a Mac as well as on a PC. So, so this is pretty good for free. Okay. Any other questions at this point? So, were there any questions with respect to the homework that you had done previously? Exercises. I know that there were a number of questions that had come up in the Discord conversations that had happened, and I have a concern about some of those. Series parallel was one of your circuits, circuit analysis. You had a circuit I that you had to measure currents for, and more than one person blew up their current fuse. It's bound to happen. I mean, it's an accident that's going to happen for infrequently, but when it does, you just have to buy a new fuse. So at least 2 of our classmates had fuse issues. Current dividers, you certainly had a lot of practice. Voltage dividers and current dividers. There was a question that came up, interestingly, and I made a notation for some of you about the diameter of the wire. 2 people asked me the question to help clarify that, and I'm surprised more people hadn't. They had done a calculation. And for the diameter of the wire, no, you don't have to calculate area. It's a really, really simple exercise. You start off with a diameter of the wire that's 40 millimeters. Diameter is the cross-sectional measure from one side of the circle to the other. And 40 millimeters is how many centimeters? 4 centimeters. And then it says that the wire diameter changes. So the wire diameter has now gone from 40 millimeters down to 2 centimeters. Well, initially your 40 millimeters had to be changed to 4 centimeters. And so the diameter went down by a factor of 2. But if you draw this out on a circle, the diameter changed from 4 down to 2. So the area decreased by a factor of 4. It's 1/4 smaller now. A 4 centimeter circle would be this big. A 2 centimeter circle is about 1/4 of that. So all you had to do for that particular exercise is basically calculate your current, calculate your ohms, your ohms at 45 ohms, and reduce that by a factor of 4. A lot of people reduced it by a factor of 2. You reduce it by a factor of 4. There was another question that was really fun and interesting, having to do with the cost in kilowatt hours. If you pay for your own PG&E bill, you got to know PG&E charges you in units of kilowatt hours. So the lamp was 750. Oh, so microwave was 700. No, lamp was 175 watts. You convert 175 watts to 0.175 kilowatts, then multiply by 24 hours, and then you will end up with an answer that's less than 76 cents. It works out to be 75.6 cents. So there's some interesting things that you had to think about or ask about. The other stuff is pretty straightforward. I don't think there was any issue anybody had with any of the other stuff. On the homework questions, let's see if there were any particular challenges there. You got to read my notes, because if you had less than 100% of your points, if this was a 50-point exercise, you ended up with a 42, you got to read my notes. Why did you get a 42? So far, there has been no late penalty for any of you for turning in anything late. So the points do not reflect anything turned in late. The points deducted reflect some errors that happen along the way, and I made notes for each of you where those errors were. And if you have to read those notes, because you have a test coming up in a week, and you don't want to be making the same mistakes in your homework on your test as you did in your homework. So let's see, everything else was pretty straightforward. Then we get to the series parallel. And were there any particular challenges that people experienced with respect to series parallel? Part of the circuit is in series, part of the circuit is in parallel. So you can't make all the currents the same. You can't make all the voltages the same, because it's not a pure series circuit. It's not a pure parallel circuit. So I saw some people make all the voltages the same, some people make all the currents the same. No. It's a series parallel. And you have to, if you watch the WISC video, if you watch it and you play it all the way through, it's like 8 minutes to watch it all the way through. It walks you through step by step how to do that particular exercise. That exercise will be part of your test. You got to know how to solve series parallel with some degree of confidence. That's not hard. Watch the video, and if you have any questions along the way, you know to ask me in Discord. I think that's all I needed to say about the homework. That was all right. Now we're going to do something fast. So back to my share screen. All right, File, New. Okay. All right, so I'm going to drag a voltage source. I'm going to magnify this a little bit because I like a little bigger image. And I'm going to drag out 3 resistors. And I'm going to rotate this particular one. And I'm going to put a ground in here. So let's go ahead and put a ground over here. Deselect. And I'm going to connect this guy to this guy. I'm going to connect this guy to this guy. I'm going to connect, hover. Come on, be nice to me. Be nice, hover and connect. Good. Deselect and hover and come over. Good. And do one more. Hover over and connect. Oops. What a mess. Where's this guy going? Okay. Eliminate. All right, it's gone. I'm going to double click on this guy, and I'm going to make this guy 300. I'm going to make this 3,800. Double click this guy and make this guy 2,100. Double click this guy and make this guy 7,100. 7,100. and double click this guy, and I want to change the frequency to 2.6K, and I'm going to change the voltage. I want the voltage here to be 15 volts. Boom. All right. Pull out your paper. Let's do a VIR very quickly. VIR. 3800, 2100, 7100 at 15 volts. Okay. Find your R total. 800 plus.
Professor, is this VP or VRM?
V peak.
Thank you.
Thank you. Okay, so 3.8 plus 2.1 plus 7.1 equals, yes, 13 is good. So divide by. Okay, confirmed. Remember to double check. Recalculate your current more than once. Make sure your RT is good, because if either one of those is wrong, we're going to be crying the big tears. Voltage. Voltage. And voltage. Okay, and when I add these two together, get 62. Okay, cool. All right, the calculation's done. Now, let's go ahead and place my probes. So I'm going to do a voltage probe there. Grab another voltage probe, put it there. Grab another voltage probe and put it there. Cool. So 3 voltage probes were fine. And everything looks good. All right, I want to do a split. This can be narrower. This can come over to here. Okay, and let me run this. Waiting for data. It's now run. While it's running, I've got too many cycles on my display. Change to something that's more readable. Pause it for a moment. Yeah, that's pretty readable. That's good. Very good. All right. While this is here, my cursors come over to cursor on the y-axis. And before I pop my cursors in place, we need to have a target and understand what kind of voltages we expect to see. For a 15-volt source, who would like to volunteer the voltage for R1? How much voltage do we calculate for R1?
4.37 volts.
Harpreet says 4.37. Yeah, that's pretty close. I get 4.38 because I'm using all memories, but that's fine. So Harpreet, good job. 4.37, 4.38 volts. I'm looking for a VR2 from another classmate.
2.42 volts.
Ephraim says 2.42. Ephraim, 2.42 volts for VR2 is correct. I'm looking for a volunteer for VR3.
I got 8.17 volts.
Benjamin comes in. Benjamin, there you are. Benjamin comes in at 8 point what?
8.19.
8.19 volts is correct. Okay. Now, those are the voltages across each of the resistors, just doing a simple One of these, a simple VIR chart. Doesn't take long for us to do. We've done this many times. Now, how about the voltage at A? How about the voltage at B? And how about the voltage at C? These are very specific points. The voltage at A would be your PR1. So who volunteers a voltage at PR1?
I got 15.
So Luis volunteers a voltage at PR1 of 15 volts peak, and that would be correct. Who would like to volunteer a voltage at probe number 3, PR3? Probe number 3. Who would like to volunteer a voltage at probe number 3? If you're trying to speak and your mic is muted, I can't hear anything. Nobody can volunteer a probe voltage at PR3?
8.19 volts peak.
Just excellent. There, it turns out, my friends, that probe at point 3 is the voltage of the R3 volts, R3 resistor. Okay, so the probe at point 3 is the voltage across R3 to ground. Now, a more interesting one is how much will the voltage read at probe number 2? Who can volunteer that? You should have 10.62 volts. Okay, you should have 10.62 volts because that is the sum total of voltage across R2 and the voltage across R3. Those two add up to 10.62 volts. So your VA is at 15. Your voltage at point B, your second probe, is at 10.62. And your voltage at point C, which is probe 3, is at 8.19 volts. With that information written down, I will now move the cursors to confirm. All I need to move is just one cursor. I don't even need cursor number 2. I just use cursor number 1. Without using the cursors, just looking at the vertical scale on the left-hand side, where do you see that green waveform peaking at? Is it peaking on a line right here? And is it associated with this 15-volt marker on the left-hand side? Yeah, it's 15 volts just by virtue of reading it right off the graph. The other two waveforms, however, are harder to read off the graph because they don't line up with any of the graph markings. Here's where you do need a cursor. So I'm going to grab the cursor and I'm going to move it above the light blue. And we expect what, 10.62? Let's see what happens here. Move it right to there. Cursor number 1. I expect 10.62. What do I get? 10.676. Pretty darn good. Are we happy with that? How about the voltage across the probe number 3, which is the dark blue waveform? We predicted 8.19 volts. I'm going to move this cursor down to the top of the dark blue waveform. And we expect 8.19. What do we have? 8.26. Pretty darn close. We're happy. Okay, in the real world, we're happy because there's some tolerance. Even in the simulators, there's some tolerance. Are we good with confirming the voltage values? Now we want to confirm the time. Okay, and to confirm the time, I have to change my cursors from the y-axis to the x-axis. And I'm going to move C1 over to here. Best as I can, right there. So what I've done is I've moved C1, and do you see a little circle that follows the intersection of C1 with the green waveform? Do you see that little circle riding along the waveform? I want to move this until that circle goes all the way down to the 0 line. Right, went below. Move it right. Had it for a moment, and then I moved it. Okay, right there. Whew. All right, now I'm going to move the second cursor right here. All right, and the time difference between these two, my delta x is given right here. My delta x is my difference of time between the two. It is given as 384 384.96 microseconds. That is the time for one cycle. Key that into your calculators right now. Key in 384.96 84.96 micro. So second exponent -6, and enter that. While you have the number of microseconds, the time entered, can we immediately calculate frequency by reciprocating this number? So hit reciprocal key and hit enter. And what do you calculate? Your calculator should show you 2.5976. Is that pretty close to 2.6 kilohertz? Wasn't 2.6 kilohertz our set frequency? Does the O-scope here show you the reciprocal of 1/x as 2.5977 kilohertz? Is that pretty darn close to your set frequency of 2.6 kilohertz? This is a remarkable free online O-scope circuit simulator. Everything we've done in TINA, we can do here and more. Okay? So you really can't appreciate this until you've done the TINA circuits. But once you've done the TINA circuits, you say, oh man, now I can do this much more because I can't do this in TINA. All right? Any questions about this? We've gone through 2 examples with this particular guy. I'm really excited that we had the time to do this. Any questions? Okay, so what should you do?
Wait.
What?
So I got lost on the 3 probes that we made.
Yeah. You know where I got them from? You want to see where I got them from? I'll show you where I got them from. Okay, let me hit stop because this is, okay. So I have to stop the simulation. So the probes came from our menu on the far left, and the probes are this green dot at the top. So when I click this guy, I can select a voltage probe, a current probe, other kinds of probes. I'm just going to select voltage. So I click and yank this guy out, and I can place this anywhere. So now I've grabbed the 4th probe, and now I've got probe number 4. So that's where I grabbed the probes from. Did that answer your question, where they come from?
Or not really, because then we had predicted peaks. Was that what was said earlier?
Yes, we had predicted peaks, which are right here. Okay.
Not from the VIR chart.
Okay. So the predicted peaks. Yes. Okay. I understand what you're exactly what you're getting at. Let me help you out with this. Let me add one more thing to this computer that I didn't have a moment ago, and bring in this camera so that we have this here. And let me switch the video from the wrong mouse. That's what happens when you have 2 computers on the desk. Okay. Let's go to here, and let's go to here. Okay. Can everybody see my VIR chart? My VIR chart should look like your VIR chart, or your VIR chart should look like mine. You have your resistances, total, current, you double check the ohms total, you double check the current total, then you fill in the current column. After you fill in the current column, you multiply, and you end up with these voltages. So are we happy with these voltages so far?
Yeah.
Done. Now, we want voltages at specific points with respect to ground. Now, in order to get voltages at specific points with respect to ground, we have to look at our circuit. So our circuit was AC source. So here will be a resistor, a point. Here will be another resistor, a point. Here will be a last resistor, and we have ground down here. So we said that we would have 4.38 volts here, 2.42 volts here, and 8.19 volts here. This goes to the very heart of what we did last week in terms of our labs, when especially this, I think there was circuit G, because you had to know with confidence how much voltage you had, very specific points with respect to ground. This point will be A, this point will be B, this point will be C. So if I am looking for VC to ground, and the top of this is positive, this is positive, negative, positive, negative, positive, negative. At point C to ground, where's my ground? Way over here. Is my ground also here? Same point, yes? So between C and ground, I have my red probe here, I have my black probe here. What do I expect? What do I see between these two? Don't I see the 8.19 volts? So my voltage at point C is going to be equal to 8.19 volts. So VC equals 8.19 volts. Now, how about voltage at point B? The voltage at point B says that I have to have my red probe here. Where's my ground? Still over here. Do I have voltages between the red probe and the black probe? Clearly I do. And so what do I have between the two is I have
The sum?
the sum of the two.
Okay.
And the sum of these two worked out to be the 10.62. 10.62 volts, so that's 10.62 volts. And then the voltage at point A means my red probe goes way over here. Well, what is the sum of all three? Isn't that equal to my 15 volt peak? Okay, so that's where these voltages came from. Okay, voltage at the first probe, voltage at the second probe, voltage at the third probe came specifically from our exercise in circuit G last week. And knowing what voltages we expect at specific points, our reference is ground. All we have to do is keep our black probe at ground and just move our red probe from here to here to here, which on our oscilloscope, we did this way. Wrong mouse. I keep grabbing the wrong mouse. Come back to no, that's me. Are you on the share screen? Can you see my, can you see?
Yeah, I can see it.
The simulation? Okay.
Yeah.
All right. So if I go back to run this and my cursors, I readjust this for y-axis and then I stop. And my cursor, I move this up to here. I have 14.959, very close to 15. If I move my cursor to the top of the light blue, I expect something like 10.6, and I get 10.659. And I move this here, I get 8.19, I hope. And let's see, stop right there, and I get 8.1957. So the cursors, because they're straight lines across, they touch the tippy tops of each of these waveforms, we're able to confirm what's at point A, what's at point B, and what's at point C. So this is a really remarkable piece of software that we can very quickly find our way around doing what we need to do.
Okay, well, that definitely helped. I think I got confused on the schematic side.
Yes.
Where you paused it, I was looking at those numbers, but they fluctuate because it's AC. So I was trying to compare those numbers to the predicted numbers, and they weren't matching at all.
No,
Yeah.
that they weren't.
That's my mistake right there.
Until I stabilized and stopped everything.
Yeah.
So right now, the waveforms conform to our calculations of our VIR. So if you stay with VIR, you're rock solid with all of this.
Okay, thank you.
Okay, no, I appreciate the question. I'm glad you asked. Any other questions?
Professor, how do you zoom out? Because I zoomed in too much and I can't zoom.
You'll have to play with it. I think you have to be. Let's see. If I am here, and then I go ahead and stop. Yeah, you'll have to play with it. I don't have a fast answer for that. That if you change your scale vertically or horizontally, I know on the run mode, I can change my time base, and my time base allows me to have not enough cycles on display like this. That's not enough cycles, I need more. And then so if I change my time base here, now I've got too many cycles on the display. So while it's in the run mode, I change it to here, and I've got a very comfortable amount of sine waves on the display with enough spacing that I can do my measurements with some degree of confidence. Now, if you've got your vertical scale changed, you're going to have to play with that. This is new for me also. I'm really used to playing with regular multisim.
Sounds good, thank you.
So what I'm going to do here is, since we've done so much work, I'm going to do a save as. And on the save as, this is again AC. And this is 3R And I'm just going to type IMA -2 because I've already got another AC3R. And now you save it. And then from here, you can do screenshots and then paste into a document and upload and send it to me. So I want to give you some time to practice and play with this. Certainly download your circuits challenge as presented earlier this evening. Get going on those, save your certificates, and save up your questions for Thursday. So we have an hour Thursday for your questions between now and Thursday. So definitely dive into this stuff, okay? Cool. I will sign off then. I wish everybody, unless you have a question, I will sign off and stop the recording. I will stick around for anybody who has some remaining questions, but I'll stop the recording now. And I'll say goodnight to